Very well. So let us continue what we learned last week. We are still in chapter 11. We have a lot of contents to cover. We start talking about sequences. Then we said those objects are not very interesting. So let us create some new objects that we call series. Chapter 11, 11.2, continue. Objectives, series. So let us review what we learned so far. Recall that. We start talking about sequences. A sequence is a function, it's just a function, a sub n equals to f of n. It's similar to the function that you learned in elementary calculus, but the graphs are discrete graphs. We can list the terms of the sequence as a sub 1, a sub 2, a sub 3, a sub 4, and so on, and we can graph it. For example, a sub n or f of n is equal to 1 over n. We can plug in different values for n and find the terms of the sequence: 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And we can visualize the graph as n gets larger and larger. So at 1, you have 1. This is a sub 1. At 2, you have a half. At 3, you have a third. At 4, a fourth. And this is the behavior of this sequence. Remember that when it comes to sequences, we're interested in the behavior of the sequence as n goes to infinity. So we say that the limit of this sequence as n approaches infinity, 1 over infinity, is 0. Well, it's not very interesting to have just sequences. As mathematicians, we're interested in creating some new mathematical objects. New objects. How do we create these new objects? By adding the terms of a sequence, we create series. The sum, a sub n starts from 1, goes to infinity, which is a1 plus a2 plus a3 plus ... is called a series. Okay, so when we're talking about series, we're interested in knowing when we have a convergent series and do we have a divergent series. So the technique that we came up with is to use partial sums. We say that, hey, S sub n as the partial sum is equal to the series A sub I. So wherever we see n, we use I. I starts from 1 and it stops at n. So these partial sums actually constructs a sequence. How so? S sub 1 is just a sub 1. S sub 2 is just a sub 1 plus a sub 2. S sub 3 is a sub 1 plus a sub 2 plus a sub 3. And S sub n is a1 plus a2 plus a n. We take this sequence. We say that if this sequence is convergent, then we say that this series is convergent. So if Sn as a sequence is convergent, then we say that our series is convergent. Much more work to do when it comes to series. For example, Let us take the elements of previous sequence and create a series. So S sub 1 is going to be 1 over 1 for just 1. S sub 2 is equal to 1 plus a half, 3 halves. S sub 3 is equal to 3 halves plus a third, 11 over 6. Last time I made some mistakes here. Then S sub 4 is 11 over 6 divided by 1/4, which is equal to 50 over 24, and so on. So this is the graph of our sequence 1 over n. Now we're interested in graphing this new sequence S sub n. Well, S sub n, the very first term is 1. The same here. S sub 2 is 3 halves. Okay, this is S sub 2. Then S sub 3 is 11 over 6. It goes here. Then you have 50 divided by 24. Goes here. And so on. This is your sequence S sub n. As you can see, 1 over n as a sequence is convergent to 0, but S sub n, it gets larger and larger in y values. So S sub n for this series that we have a name for it, harmonic series is that example. Harmonic series, the sum 1 over n starts from 1, goes to infinity, is divergent. Very well. So I expect you to ask, do we have a theorem that helps us to analyze the series in the beginning steps? We have a theorem that says if a series is convergent, then the limit of the general term must be 0. So let's write this theorem down. Theorem. If series sigma a sub n starts from 1 to infinity is convergent, then for sure you can say that the limit of general term a sub n as n goes to infinity is 0. Okay. For those of you who know logic, its contrapositive is, so if the limit of an while n approaches infinity, it doesn't exist or is not equal to 0 in general, then for sure you can say that your series is not convergent. If the limit is not equal to 0 or the limit does not exist, then the series starts from 1 to infinity is divergent. So always check this if the limit is not 0 or it doesn't exist. Then you can quickly decide about the series itself. If the limit of general term is not 0 or it doesn't exist, then for sure you can say that the series is a divergent series. Quick note. What if the limit is equal to 0? Can we say that the series is convergent all the time? Be careful here. Note, we cannot say that if the limit of an as n approaches infinity is equal to 0, then the series in general is convergent. We don't have a theorem or lemma about that. Actually, we have a counter example. The counter example is, you know that the limit of 1 over n as n approaches infinity is equal to 0, but the harmonic series is divergent. So make sure that when the limit is equal to 0, you are using some tests to make sure that your series is convergent or divergent. Very well. So we came up with nice theorem and it's contrapositive to help us analyze some series. But among all of the series that we're going to work with, some of them follow this theorem. Many of them, the limit of your an is 0, and you have to check your series. Very well. Let's take a look at these two examples. First example says, which one is convergent? The first one is the series n squared divided by 5n squared plus 4, n starts from 1, goes to infinity. And the second one is series, the sum, what do we have here? 3 over n times n plus 1 plus 1 over 2 to the n, and starts from 1 and goes to infinity. Okay, so in this case, an, the general term, is here. When it comes to series, the very first step is to check the limit of the general term. So step 1, check the limit of an as n approaches infinity to be equal to 0. So let's check this guy. So we have the limit of n squared divided by 5n squared plus 4 as n approaches infinity, which is, so you ignore the smaller term. You have 1 divided by 5, 1/5, which is not 0. So you quickly say that since the limit is not 0, it means that the series is not convergent. So we do not move on to step 2. Step 2, no need to, because it doesn't pass the very first step. Step 1, the limit is not equal to 0. So it's not necessary to go to the next step. What about this guy? Okay. Step one, let's check the limit of an. What is an? An is, here is the sum of these two quotient. Okay, it's not very hard to analyze this. We have 3 divided by n times n plus 1 as n approaches infinity plus 1 over 2 to the n. As n approaches to infinity, you have 3 divided by infinity. This is 0, and 1 over 2 to infinity, which is again 0. So the limit is 0, and we can move on to the next step. Step 2. Check to see if the series is convergent or not. Okay, let's see. Let us analyze the very first series, then analyze the second series. You can split these two series, of course. This series is not very hard to analyze. We talked about it before. This is geometric series, but what about this guy? Can I write it using telescopic series? Let's write them down here. The series 3 divided by n times n plus 1 can be written as 3 times the series 1 over n times n plus 1. And starts from 1, goes to infinity, 1 to infinity. Remember that our job is to analyze the partial sums. So Sn is equal to, I'm going to keep this 3 outside the series and just analyze this series here. This is just a scalar. This is just a number. This is just a constant. So let us leave it outside. S of n is equal to the sum 1 over I times I plus 1. I starts from 1, goes to infinity. I'm going to use partial fractions to split this. So S of n can be written as the sum 1 over I plus 1, and I starts from 1 to infinity. So I took this one fraction and I split that into 2 fractions. Well, now I'm going to plug in values here. Let me see. S of n is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus dot, 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 1 over n minus 1 minus 1 over n plus 1 over n minus 1 over n plus 1. So as you can see, we can cancel out opposite terms, negative a half, negative a third, 1 over n minus 1 with the previous term, which is opposite, negative 1 over n and 1 over n, and you're left with 1 minus 1 divided by n plus 1. Now let us take the limit of S of n, this sequence. As n approaches infinity, this is equal to 1. So the limit of the partial sums is 1. So our series, which is series 1 over n times n plus 1, starts from 1 to infinity, is convergent. Is convergent to 1. Okay, it has a 3 in front of it, so you get 3 times 1 as the sum of this series. So far we have this. You have this guy is 3, 3 divided by n times n plus 1, and starts from 1, goes to infinity. It approaches to 3. This guy, this is easy. You saw this series before. It's a geometric series. So the sum 1 over 2 to the n, and starts from 1 to infinity, is equal to a half divided by 1 minus a half, which is a half divided by a half, which is 1. So if I add 3 and 1, the sum is 4. So this series is convergent to very well. So give us more techniques. We're going to connect series and integrals. Use the integral to check to see if we have a convergent or divergent series. So when you see a series, first check to see if you can use geometric series, or maybe you can apply telescopic series technique. Then try to see if you can apply integral test. We're going to talk about it today. So integral test says if a sub n, you know that this guy is a function. If this function is positive, continuous, and decreasing, on 1 to positive infinity, then you can construct the integral. Then your series a sub n, and starts from 1 to infinity, is convergent if and only if, if and only if the integral 1 to infinity f of x dx is convergent. And your series is divergent if and only if this guy is divergent. If and only if the integral 1 to infinity of f of x dx is divergent. Okay, give us an example. Take a look at this example. Analyze the series 1 over n squared plus 1, and starts from 1 to infinity. Okay. So remember, our step 1 was to check to see if the limit of an as n approaches infinity is equal to 0. If it's not 0, we don't bother to go to the next step. So the limit of an is the limit of 1 over n squared plus 1 as n approaches infinity, which is 0. So we're allowed to go to the next step, step 2. Now check your series. check the series. So is it a geometric series? No. Is this a telescopic series? No. What if I can check to see if integral test is working or not? Integral test says, first of all, your AN must be positive, continuous, and decreasing. If your AN or FN has these three characteristics, you can form the integral. Okay. So, integral test. So, first of all, f of n must be positive. Yeah, it's positive. On the denominator, you have n squared plus 1. It's always positive. On the numerator, you have 1, always positive. So we don't have any problem with f of continuous. Yes, of course, f of n on its domain, 1 to positive infinity, is continuous. You can graph it using Desmos. Is it decreasing? To be decreasing, let us take the derivative of this function. Remember that you can either apply the definition, n is less than n plus 1, then f of n is larger than f of n plus 1, or you can take the derivative. So the derivative of f is going to be, here you're using quotient rule for an. The derivative of 1 is equal to 0 times n squared plus 1, which is 0, minus 2n divided by n squared plus 1 squared. Okay, on the numerator, I have a negative sign, and my domain is 1 to, where's my domain? 1 to positive infinity. So if this guy is definitely negative. So the derivative is negative. What's the meaning of that? It means that your function is decreasing. Since f prime is negative, so f is decreasing. So it meets all of three conditions for the integral test. Okay, let us apply the integral test then. I'm going to construct the integral of f of x while x ranges between 1 to infinity. So the integral 1 to infinity of f of x, 1 over 1 plus x squared dx. You all know that this guy is inverse tangent. Tangent inverse of x, 1 to infinity. So you have inverse tangent infinity. It means that you have sine over cosine. It must be pi over 2 minus, it is 1 as pi over 4, and this is pi over 2. So since the integral is convergent, it means that your series is convergent. Please fix that. It is pi over 4, not pi over 2. Another example that we're going to use is actually very famous. They have a name for it. They call it P series. But it's actually using the integral test for those types of series. So definition of P series. expression P series. Series 1 divided by n to p as n approaches to infinity is called a P series. A P series. Try not to confuse P series with geometric series. So here you have, for example, if you write this in expanded form, you get 1 divided by 1 to the p plus 1 divided by 2 to p plus 1 divided by 3 to p plus the rest of it. So it happens that if p is larger than 1, you get a convergent series. And if p is less than or equal to 1, we have a divergent series. When p is equal to 1, you actually saw the example. We call it harmonic series. So note p equals to 1. We have harmonic series. Geometric series, telescopic series, integral test, and P series. So far we learned about these 4. Okay, give us example. Example. Analyze the following. The first one, well, here we have the sum 1 over n cubed, n to the third, and starts from 1, goes to infinity. And the second one is the sum n to a third, 1 over n to a third, and starts from 1 to infinity. Okay. Is this geometric series, either of these? No. Telescopic? No. Integral test? Okay, let's see. It's worth it. Integral test, and recall that we already know that if we take the limit in step 1, the limit is 0 for both cases. So they're allowed to go to the second step. So integral test. Integral test, we need to check to see if this an satisfies all of those 3 conditions. Fn is positive, of course. So n is 1, n is 2, n is 3, all of those sequence terms are positive. Is this continuous? Yes. On 1 to positive infinity, it is continuous. Is it decreasing? Okay, let's take the derivative. The derivative of f is equal to -3 into -4, or -3 over n to the 4th. As you can see, the derivative is negative, so it is decreasing. So it satisfies all of the conditions. Now we can take the integral. Integral 1 to infinity of 1 over x cubed dx, which is -3 over x to the 4th, 1 to infinity, which is equal to, so this guy over infinity is 0, minus -3 over 1, which is 3. Since the integral is convergent, so as the series. Integral is convergent, so as the series. Or you could say that, hey, I have a P series. This is 1 divided by n to the p, and p is larger than 1, so it is convergent. So either use the method of integral test or use the definition of P series. P series, P is 3 larger than 1, so it is a convergent series. As you can see, for one series, we can apply multiple techniques or definitions. Obviously, by using the definition of P series, P is equal to a third, which is less than 1. So using the definition of P series, which is coming from the integral test, if you take the integral of this function, the integral diverges, or in simplified form, using the definition of P series, since P is less than 1, so our series is divergent. Well, the next technique is using comparison test. Okay. So geometric series, telescopic series, integral test, P series. Now we're going to talk about comparison test. What is comparison test? Let me give you an example, then I'm going to write down this test for you. Suppose I asked you to analyze these series. Analyze the function. I have A, the sum, 1, no, it's 5 divided by 2n squared plus 4n plus 3. And another one, be the series 1 over square root of n plus 1, n starts from 1, goes to infinity. Suppose I ask you to analyze these two series. So you take a look at your instruction. Is it geometric series? Of course not. Telescopic series? Nothing like a telescopic series. Integral test? Okay. For integral test, I have to go through a lot of steps, check to see if it's positive, if it's decreasing, if it's continuous. Might be able to use integral test. So I'm going to put a question mark. So no, and a question mark. P series, of course not. It's not a P series. The definition of P series is the sum 1 divided by n to the power p. It doesn't have too many terms. So it's not a P series. Comparison test. Comparison test says, okay, if you have a complicated series, compare it with one of these series, like geometric series and P series, like this. Comparison test. Let two series, AN and BN, be two series with positive terms. Only positive terms. You have two cases. If AN is less than equals to BN, and so AN is less than equals to BN, and the series BN is convergent, then the smaller series is convergent. If AN is less than equals to BN and the smaller series is divergent, then the larger series is divergent. So note that what are we doing? AN is less than equals to BN and the larger series is convergent, so as the smaller series. AN is less than equals to BN and the smaller series is divergent. Smaller series is divergent, so as the larger series. Okay, how can I apply that here? Do I know any known series that I can use? There are tons of different series that we can use. Based on the given series, you can try to find that known series. So I'm looking at this series. This starts from 1 to infinity. If I ignore the terms with lower exponents, like 4n plus 3, this is a linear expression. If I forget about this, this is 5 divided by 2n squared, which is 5 over 2 series 1 over n squared. I get a p series which is convergent. Keep that in mind. You have a complicated series. On the denominator, you have a quadratic expression. Ignore the linear part. What's left? You have 5 divided by 2n squared. So it seems like you can use a p series, which is a known series for comparison. So since AN, which is this series here, 5 over 2n squared plus 4n plus 3 is less than equals to 5 divided by 2n squared. This is your Bn. And the series Bn is 5 over 2, 1 over n squared. And this guy is a p series and convergent. 2 series or p series and convergent. Which case is this? My larger series, I'm using the same color. My larger series, my p series is convergent. My larger series is convergent, so as my smaller series. So as our series. So this series, you can quickly say that by using comparison test is convergent. Very well. So as you can see, for this guy here, we can use comparison test. Use comparison test and compare 1 over square root of n plus 1 with 1 over square root of n. Then you already know that this guy is a p-series. This is 1 divided by n², p-series. And using the definition of p-series, it's divergent. So when we say an is less than bn, it means that the graph of an is below the graph of bn. It means that we are comparing the y values. As you can see, as we go along, the y values for bn are larger than the y values for an. So an, which is this red graph, is smaller than this blue graph, which is your bn. So as you can see, as bn converges, your an must be a convergent function.
So when we show that
Very well. More tests. The limit comparison test is another version of comparison test, but it deals with limits. Okay, perfect. Limit comparison test. So it says again, suppose an and bn are positive sequences. Let series an and bn be series with positive terms. Okay, now you construct the limit of, for example, an over bn as n approaches infinity. If this guy is equal to a number, c, and this number is positive, so you take the limit is equal to a number. I'm not talking about infinity, number. And that number is larger than 0, then these two, their series are both convergent or they are both divergent. Then either sigma an and sigma bn are both convergent or they are both divergent. So our next one is limit comparison test. For example, suppose question says, analyze this. The first one says, hey, you have the series 1 over 2 to the n minus 1, and starts from 1, goes to infinity. And the second one says, you have the sum 2n squared plus 3n divided by square root of 5 plus n to the 5th. So is this guy a geometric series? It's not geometric series, but it's similar to geometric series. So if I ignore this negative one, the constant, I get a geometric series. So my best option is to compare it with geometric series 1 over 2 to the n. This is geometric series. R is equal to 1/2, and it is convergent. Okay, so I have a convergent series. Now, let us use limit comparison, because I'm going to take the limit of 1 divided by 2 to the n minus 1 divided by 1 divided by 2 to the n as n approaches infinity, which is 2 to the n divided by 2 to the n minus 1, n goes to infinity, which is 1. So C is positive, it is 1. So it means that these two series are either both convergent or both divergent. Since I have a convergent geometric series, this series must be convergent. So you can write since C is positive, so both series behave similarly. And since geometric series 1 over 2 to the n is convergent, so as our series. So I'm going to write down this guy here. I need more space. So B is this series 2n squared plus 3n divided by square root of 5 plus n to the 5th, and starts from 1, goes to infinity. Okay, so as you can see, this guy is not geometric, it's not telescopic, integral test. Oh my God, I have to take the derivative of this guy, check to see if it's, negative, decreasing, and then you have to take the integral. No, thank you so much. I'd rather go to the next one. P series, it's not a P series, either comparison test or limit comparison test. So first of all, we have a series and we need to find the series that we already know what the behavior is. What I'm going to do, I'm going to ignore the terms with lower power on the numerator and on the denominator. So on the numerator, I'm going to ignore the term with lower exponent, which is 3n. On the denominator, I'm going to ignore the constant. What's left? 2n squared divided by n to the 5th, which is 2 divided by n to the 3rd, which is a P series, and I already know how to deal with it. So to find the second series, ignore the terms with lower exponents. So on the numerator, I end up with 2n squared. On the denominator, I end up with n to the 5th, which is 2 divided by n to the 3rd, which is a P series, convergent P series. Okay, I found the series that I'm looking for, and it is convergent. You can either apply comparison test or limit comparison test. Let us apply limit comparison test. The limit of 2n squared plus 3n divided by square root of 5 plus n to the 5th divided by your P series 2 divided by n to the 3rd as n approaches infinity. We're getting back to elementary calculus, finding the limit. So this is the limit of, we're going to multiply these two together, n to the 3rd, 2n squared plus 3n divided by, multiply these two, 2 times square root of 5 plus n to the 5th as n approaches infinity. Since n approaches infinity, we are only dealing with the largest exponents on the numerator on the denominator. So this limit is the same as the limit of 2n squared times n to the 3rd divided by 2 times n to the 5th. As n approaches infinity, this is 1. 1 is equal to c, and c is positive. So they behave similarly. Since c is positive, so they both behave similarly. Since series 2 over n cubed and from 1 to infinity is a convergent P series, so as our series.